The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, good evening, folks. Thank you so much for joining us for another episode of our Best Practices webinar series with 7Signal. If you could let us know where you're tuning in from, that would be awesome in the questions panel. I see we have a few people already tuning in here. I am actually in the Cleveland office today, up in our headquarters, and we have Jim who is joining us from Cincinnati. Is that right, Jim?
That's right, Kelsey, just up a little bit north of Cincinnati and Oxford, where it's a beautiful day.
Beautiful day as I'm sitting here in gloomy Cleveland where the weather is getting colder and the leaves are changing.
Oh, really?
Oh, yeah, it's full fall mode
It's
here.
70 degrees and sunny down here.
Oh, my goodness. I miss Cincinnati, I'm not going to lie. All right, well, thanks for tuning in, Jim. We have a few people who are dropping in where they're joining us from. I see we have Germond joining us again from Norway. Welcome back. We have Jeff joining us from Galleon. We have Tom joining us from Cleveland. Thank you, Tom. All right, so we have Paul joining us from Pennsylvania. Welcome back, Paul. All right, awesome. Thank you, guys. And I see a few more people dropping in. We'll check in with you guys later during the Q&A panel and let us know where you're joining us from. So we are 7Signal, the leader in wireless experience monitoring, and we'll go a little bit more into depth as to how that connects and aligns with our 7Signal mission as well. So today we have a great topic, basics of 802.11 arbitration. A lot to unpack there. We have a really exciting presentation today with Jim Vada, who is joining us, as we said, from Cincinnati. Jim is our Director of Global Wi-Fi Solutions here at 7Signal and CWNE number 183. Thank you, Jim, for joining us.
Good to be here. Thanks, Kelsey.
Awesome. And my name is Kelsey Rizzuto. I am a marketing specialist for the 7Signal team. Really excited to be back here again for this webinar and really excited to dive into this topic today. So we'll go ahead and get started. A couple of announcements, some housekeeping before we begin the presentation. A lot of these will sound familiar, but we do partner with CWNP for every single one of our webinars. So if you're pursuing a certification, and by watching these webinars every week, you are eligible for CE credits. So just shoot us an email, drop us a message, and we'll be able to quickly send you over a certificate for that as well. We also host a product tour every single Friday at 12 noon Eastern. Go.7signal.com/tour. And we will go ahead and drop that link in the chat during the webinar. So if you're interested in registering, you can go ahead and do that. Now, we don't get too deep into the product or any kind of demo on these kinds of webinars, but we do have a couple of exciting announcements here just to kind of fill you all in. We recently announced yesterday, actually, our release of MobileEye for iGel Linux. In the past, we've also added enhancements to Sapphirei over-the-air mode, and we've announced the release of a portable Sapphirei sensor this month. A lot of exciting updates there. We'll drop some information in the chat for you all to check that out. And if you haven't recently attended a product tour, we suggest going ahead and registering for one, as there's a lot of exciting new things happening with us. We also post all of our archived webinars to our YouTube channel at 7Signal. And this webinar today will also be posted later this afternoon. So you can go ahead and check it out. We're also very active on our Twitter account at 7Signal. We post our slides after every single webinar there. So if you follow us, go ahead and check that out. And if you're not active on Twitter, no worries. If you're interested in receiving today's slides, we'll be able to email those to you per request. We are also, as I said, very active on Twitter. Why we do that is we have a lot of people who are engaged with our trivia questions and follow us, and we give away swag and merchandise for that. So I'm going to go ahead and read some of last week's winners, who are some lucky recipients of some 7Signal merch. We had Matt Hato, Matt Horn, and Andrew Harrison. So congrats to you all. Thank you for following us on Twitter, for engaging with our trivia questions. You should be receiving, actually, our brand new 7Signal masks, branded masks, very popular around the office already. So
wow, I need to get one of those.
I know, Jim, you haven't even seen this yet. So you guys are the first to see. Exclusive release.
Lucky winners. That's cool.
So you three will be receiving those soon. Jim will make sure you get one as well. And for the rest of you all, if you're interested in getting some swag, go ahead and follow us and engage with today's trivia. Before we move on, another exciting announcement. We have recently been recognized in the Gartner 2020 Market Guide for Digital Experience Monitoring. We've been recognized as a representative vendor for MobileEye. We're really excited, really proud of this, and we'll go ahead and drop a link in the chat as well so you can check out some more of this information. All right, on with the show here. So a little bit of a background on 7Signal, our history. We were established in 2007 in Helsinki, Finland, and we are now located in Cleveland, Ohio. We've hit a lot of major milestones across the way. We have 1 billion data points analyzed daily, and we're really proud of the 5 million devices we're monitoring daily as well. We have over 200 customers, over 30 partners, and 14 patents, which ultimately means that the technology you see from 7Signal, you are only going to see from 7Signal. We're also certified in over 40 countries, and we are GDPR compliant, which means that we take privacy and data very, very seriously for all of our users across the globe. All right, here at 7Signal, as I said, our mission is with wireless network monitoring because we understand that the digital experience and productivity of your users depends on connectivity. So what we are able to do is to gain full visibility into the end user experience through an outside-in approach. We're also completely AP and device agnostic, which means that the great tools, great technologies you already have installed on the network, we're incredibly complementary with as well. So what we're able to do with that full visibility is to detect the top 7 Wi-Fi problems that are usually time-sensitive issues that need to be resolved quickly for your users, such as congestion, coverage loss, roaming issues, adapter and driver issues as well. And how we're able to detect those issues is by running active and passive tests on the network, looking for things like throughput, packet loss, latency and jitter, and more. So to give you a little bit of a background as to how this is so different, is you've already got with your typical enterprise LAN infrastructure, great tools, great technologies already installed on the network, such as your Riverbed, Cisco, Aruba, and more. But what we're able to do is to take it one step further with MobileEye, where we're able to gain that outside-in approach on the network, living on the edge. With MobileEye, we can ultimately be installed on any mobile device, such as your laptops, mobile phones, Zebra scanners, workstation on wheels, and more. And MobileEye can be installed on any macOS, Linux, Android, or Windows device as well. We also have our Sapphirei, which are the sensors for service level quality and RF visibility, giving you a full perspective as to what is occurring in your Wi-Fi network monitoring environment. What we're able to do with that as well as times are changing is we're able to gain visibility into your home networks. For those of you working from home today, in an apartment, at your house, we're able to gain that perspective as to what is occurring in that network as well, giving you full visibility and full reliability. As I said, a lot of you on the line, as I can see from your comments, are working from home. And that's not going to go away anytime soon. Even as we begin to move towards our new norm, some people, such as 72% of office workers, are still going to want to work from home at least 2 days out of the week. So gaining that visibility into home networks is still very crucial moving forward. In the midst of this time, we've been doing a give back to meet those new demands with our MobileEye offer of 50 devices for 50 days. And we'll go ahead and drop that link in the chat as well, so you can go ahead and check it out. All right, so as I said, we do give out merchandise for our trivia questions, those who participate. So we're gonna go ahead and launch our poll for today that Jim has provided us here. And we'll go ahead and launch that. Are you able to see this question, Jim?
Yep.
Okay, how many QoS access categories are defined by WMM? Go ahead and drop your answers in the chat here.
That is the Wi-Fi Alliance's wireless multimedia certification program.
Awesome.
Don't overthink this one.
I see a few of you still entering in your answers. I'll give it a couple more seconds here. And we are going to head and close this poll. All right, how did we do, Jim?
Great, very good. There are 4 access categories. Nice and simple. It's not crazy like DSCP. Best effort, background, voice, and video. What else do you need? So there you have it.
Awesome. Well, thank you all for participating. And we will go ahead and pass the controls over to Jim here as he gets ready for today's presentation. There we go, Jim. All right.
All right, good. Okay, so here we go. Okay, so a little bit about me. I am the Director of Global Wi-Fi Solutions here at 7Signal and a CWNE. I'm also a CCNP Enterprise, aka the artist formerly known as CCNP Wireless, and I'm a wireless network engineer by trade. There's my Twitter and my Wi-Fi blog, and my new ham radio call sign if you want to reach me out there on the ether one day. But today's topic is 802.11 arbitration. I think this is really, really an important topic. It's kind of an advanced topic, but we'll talk about just the basics today. And it's a protocol used to politely share the channel that all our APs and clients are operating on. And really, in my mind, I think of 802.11 arbitration as the heart and soul of Wi-Fi. It's connected to everything else we do in Wi-Fi: troubleshooting, design, packet analysis, protocol analysis. It's really, really important. And so, after you understand it, it kind of gives you a new perspective on Wi-Fi. So important knowledge here. And so why do we need an arbitration protocol? Well, Wi-Fi uses noisy, unlicensed spectrum. You don't have to go to the FCC and buy a license to use the spectrum, the channels that your access points and clients use. Anybody can use them. Here in the US, we use unlicensed spectrum, and Wi-Fi uses unlicensed spectrum everywhere it operates in the world. But we have to account for the fact that other wireless protocols are operating in the spectrum, not just Wi-Fi, and even analog transmitters could be blasting away on the channels we're trying to use. We also don't have a centralized scheduling algorithm like cellular technologies do. To kind of put that simply, a cell phone and the tower it's connected to, the tower really controls everything that happens in those transmissions between the phones that are connected to it and the tower. So the tower tells all the phones who's going to transmit when, who's going to receive when, who's going to go to sleep and wake up at when, and it's centrally scheduling, we call that, all the transmissions and traffic there. In Wi-Fi, we don't do centralized scheduling. It's actually a distributed decision-making process where every station, and a station is either a client or access point, it's anything with a Wi-Fi radio in it, every station has to decide for itself, can I transmit now or not? So very, very different approach. And the other challenge we have to deal with is the channel itself that we're operating on. If it's in 2.4 gigahertz, the channels 1 through 11, 5 gigahertz, we've got 36 up to 165. Whatever channel we're operating on is a half duplex medium. So that's really just a fancy way of saying only one station can transmit at a time, and that station can't hear its transmission to verify that it wasn't interfered with. So this is just exactly the way simple walkie-talkies operate. And so, when you press that button to talk, Everybody else on the same channel as you hears your transmission. But actually, you're not listening to yourself. So you don't know if they heard you or not. That's why we use, silly words like Roger and over to kind of orchestrate our communication with those and confirm that messages are received. Wi-Fi does the exact same thing on the channels it operates on. And a good way to compare, to get a feel for the way Wi-Fi works is to compare it to Ethernet. So we're all familiar with Ethernet and the way it operates. It's full duplex. That means transmitting and receiving at the same time happens. It also uses a carrier sense multiple access with collision detection. That's just a fancy way of saying it knows if there was a collision when the Ethernet adapter transmitted its frame onto its medium, which is the wire. So it's kind of even, that's kind of strange language even to use with Ethernet because it's just so automatic and reliable. We never even think about, the adapter transmitting onto the wire and there being a possibility of collisions and dealing with noise. It just works with Ethernet because we plug it in and we see our port speed and we're off and running. We also don't think about collisions anymore unless you did networking back in the 1990s like I did, when you could have had multiple devices on the same Ethernet cable. Now we have switching, which breaks up the collision domain. So we only have the switch port and the device that's connected to it in the collision domain. So even though Ethernet can handle that and the protocol has CSMA CD, it's rarely needed thanks to switching. So Wi-Fi, even the latest and greatest 802.11ax generation of Wi-Fi, it doesn't have the advantages we just talked about with Ethernet. Instead of being full duplex, it's half duplex. Although perhaps in Wi-Fi 7, there will be some changes around that. Instead of having collision detection, it has collision avoidance, right? Because the transmitting station can't hear itself, so it has to do something else to just try to avoid collisions. And we have collision domains now with multiple stations participating in them, rather than just having a switch port and a device connected to it on Ethernet. Now we have all the access points and clients that are using the same channel in the same collision domain. So to put that into perspective, if Ethernet were to, a way to visualize or think about Ethernet having these same limitations would be, imagine if your Ethernet cable had just a single wire in it. It wasn't 4 twisted pairs, it was just one wire. And every device in the surrounding rooms for say 50 feet, 100 feet, were all connected to that same wire. And that wire had no shielding. So whatever interference was out there, EMI from who knows what, was just jumping right onto that wire and interfering with your Ethernet traffic. Well, that's very close to what we deal with Wi-Fi. So we have to add a lot of overhead to the protocol to account for that and do our best to overcome it. Let's have a look at the 5 gigahertz spectrum. So this is where we have the most available spectrum today. We'll have 6 gigahertz in the coming years, but in 5 gigahertz, we actually have, depending on where you are in the world, up to 25 different available channels we can use. And each one of those channels is a collision domain. And we can separate our groups of devices, our clients and access points, onto different channels so they're not contending for the same medium that APs on other channels are. And one important point from this graph, just about the use of wide channels. So the first row at the top there of 20 megahertz channel width shows us those 25 individual channels we might have access to. As we increase the channel width we're operating on to 40 megahertz, 80 megahertz, and then 160 megahertz, we cut in half the number of available channels we can use, the number of collision domains. So where spectrum is limited and we have to reuse all the channels at some point, which is very common in high density deployments, we're actually ending up with fewer collision domains. So we get the benefit of higher throughput to individual stations because of the use of wide channels, but our net system capacity is lower because we have fewer collision domains and more stations contending for those fewer channels. In other words, fewer stations are transmitting at the same time than if we could use smaller channel widths in those kind of situations. So what is the arbitration protocol we use in Wi-Fi? It's the Enhanced Distributed Coordination Access Protocol, EDCA. And basically it's the process that all 802.11 stations, APs and clients use on their own to make sure the channel is free. Sometimes you'll hear it called idle before they transmit. This came to us from 802.11e in 2005, which altered the DCF protocol by adding QoS queues to it, and that's where the E comes in. So from a high level, there are 5 steps that we're going to go through during the EDC arbitration process. A lot of acronyms here. We'll define all of them, but think of it first as we're making sure the channel is free by listening on layer 1 and layer 2. Then we're waiting a little while. Then we're counting down a random back-off timer, and then we can transmit. So the first step is that layer 1 step. That's the clear channel assessment. The next step is the layer 2 step, the checking the nav timer. And then we wait an interframe space, which is just a period of time defined in the standard. We're just not going to transmit, even though we think the medium is idle. And then we have a random back-off, which is a random number. And that way we are sort of desynchronizing all the stations that want to transmit. So only one starts to transmit before everyone else does. So let's dig into each of these steps. So the first step in the layer 1 clear channel assessment is our signal detect step. And it's called signal detect in the standard. Sometimes people call it preamble detect. That's a term I prefer, actually, because I think signal can be a little ambiguous if you're not spending all day reading the standard and you have a different understanding of what signal means. But quite literally, what the station is listening for is any 802.11 frame it can demodulate. It's listening for the preamble in that frame. And the preambles are usually able to be detected down to about 4 decibels above the noise floor. So that's a really, really low signal that can trip our CCA signal detect, sometimes called carrier sense. That's what that CSCCA means. Now, important point here, 802.11 stations have different receive sensitivity, different radio hardware, different antennas. They will not sense the noise floor uniformly. And so some stations may have signal detect tripped and some may not in the same place. The other thing in the signal detect in that preamble is that there is a length field that the station that receives the preamble can use to understand how long the frame that's being transmitted will be. So then it knows, okay, I need to wait for this X amount of time before I start sensing the medium again. Now the important takeaway about signal detect is that there is no consideration of the RSSI of the received frame. So if there's a station transmitting next to me that's minus 40 dBm, really loud, that'll trip signal detect. If there's a station, down the street that I'm just hearing at minus 90 dBm, but I can hear the preamble, that'll trip signal detect. There's no consideration of the RSSI. So the myth sometimes that you might hear is that as long as my APs are louder than my neighbors, if I've got 10 dB of SNR between the noise, if you will, of my neighbors, then I'm gonna use that and that's what my stations will use. That's not true. Anytime a preamble is detected, signal detect is tripped, and any 802.11 station, a client or access point, will back off. Moving on, so the next thing we do at layer 1 is called energy detect. This is where a station is just listening for any RF energy it can detect on the channel. So we're listening for non-Wi-Fi energy here. And this is a very insensitive threshold now, 20 dB above the signal detect threshold. So that might be, minus 75 dBm, depending on the noise floor. It needs to be kind of loud for ED to get tripped. And it's important to note too that 802.11 radios, they don't sense, they don't detect noise in any standardized way. Different adapters will do it differently and they will show you very, very different results. And so in general, we don't trust the noise measurements we get from wireless adapters. We don't, in Wi-Fi, in at least in design, we often don't talk about SNR or noise. We just talk about RSSI because that is a little bit closer to the RF truth from the adapter than what we get from the noise values. Moving on to layer 2, we've got in the MAC header of the frame a field called the duration field. That sets the nav timer. Nav stands for network allocation vector. Doesn't matter that you know that. It's just the nav timer, and it's a layer 2 timer that is set by the duration field. It can also be set by RTS request to send control, clear to send control frames that establish a period of time where a station can transmit like a burst of frames with its own access to the medium. And this is a field now that we can see in a packet capture. The preamble will get stripped out of a frame before it gets to Wireshark or whatever you're doing a packet capture with. But the MAC header's there, and you can open it up and look at the duration field. And what that's telling us, sometimes there's confusion about this. I know I've been confused in the past. It's actually telling us how much time we need after the current frame gets transmitted for the full sort of protocol exchange to complete. So that means after the frame gets, the data frame, we'll say, gets transmitted, there's an interframe space, just dead air, and then the receiver sends us an acknowledgement frame, an ACK. So the duration takes that whole exchange into account. And if you can hear the duration field now, you have a little bit more precise understanding of when the medium might be idle again. Then we do that another interframe space, and then we get to the contention window. So again, we're still listening. We listened at layer 1, we listened at layer 2, we just sat there and did nothing during an interframe spacing. Actually, we're still doing CCA during that period, but it's a still a period of time that we're just listening. And then we get to the contention window where we're still just listening. And now we have this random back off timer where we count down a certain number of time slots, starting with the values 0 to 15, so 16 time slots, each slot being 9 microseconds. So that's a millionth of a second, really, really small amount of time. And we do this because immediately after a transmission stops, every station that's waiting to transmit will be synchronized in time up to this point. We don't want them all to think the medium is free and transmit at the same time. We want to desynchronize them. That's what the contention window is supposed to do. So whoever gets the lowest slot time value counts down their contention window the fastest and then transmits. And then others that have longer slot time values hear the preamble that the station that won the frame transmitted, and then they back off and start the process over. Important to note, though, that the slot time, the back off timer, the values start at 0 to 15, but that range doubles every time a frame is retried. So if I transmit and don't get an acknowledgement back, I start all over again and get to the contention window and use a max back off timer of 32 slot times, then 64, then 128. So I'm using more, it's taking more and more dead air just to win the channel, which is inefficient. And at the same time, I'm probably dropping my data rate down, which is inefficient too, because it's going to use more airtime to use a slower data rate. So retries have some serious consequences for Wi-Fi performance. And then this is where 802.11e comes in, where we get QoS, those WMM access categories here. Those actually alter the starting values for our back-off timer depending on the voice, the QoS access category you're using. So voice, of course, is the most aggressive. It never uses a contention window greater than 7 slot time values, even when it retries. Because a voice packet, we just need to transmit and get out on the medium with the lowest latency possible. And if we can't, drop it, go to the next one, it's fine. You know, it's UDP audio. It'd be better to keep latency under control than to buffer frames forever until we can burst them all out when we finally win the channel. That's not good for audio. So that's where QoS comes into play. So finally, after all this listening and checking and verifying that and this is the process every station on the channel is doing, we get to transmit. And so I've kind of compressed that whole EDCA process here into those contention areas on this timeline. And I just want to show you what it looks like to transmit just a single data frame. So we've got the contention process, that's just dead air. Then the data frame starts to be transmitted with the layer 1 PHY header. That's where our preamble is and the length field that signal detect uses. Next, we get to the MAC header. This is our layer 2 information, MAC addresses, and the duration field that sets our nav timer. And then finally, we transmit our payload, which is probably an IP packet. You know, we're trying to get an IP packet from from a client to an access point to get out into our route switch network. We've got a frame check sequence for error correction, and then after an interframe space, we have an acknowledgement frame that comes back from the receiver. It's got a PHY header, it's got a MAC header, it's got a frame check sequence, and then after an inner frame space, we can start the whole process over again. So there's a lot of overhead here just to get that data payload out and across the medium. Just to kind of hammer that home, let's look at sort of the limitations and efficiency that are necessary because we've got half duplex medium that's unbounded, subject to interference, other protocols operating there. We never know the state of the channel moment to moment. So the contention and interframe spacing, that's all dead air. Nothing's happening, it's just dead air. The protocol requires to make sure the channel's available. Next, our PHY header with the preamble. It's actually transmitted at the lowest data rates that each band supports. So in 5 gigahertz, it's 6 megabits per second. It's in 2.4 gigahertz, it's either 1 or 2 megabits per second, depending on if you're using the long or short preamble. So you're probably scratching your head saying, no, it's not. I disabled those data rates on the controller. We don't use those anymore. Actually, you do. It doesn't matter what how the rest of the frame is modulated, which is where those higher data rates come into play. The PHY header always uses those low data rates. And 1 and 2 megabits per second, that's even pre 802.11b. That's 802.11 prime. So that's old stuff. And it'll always be with us in the 2.4 gigahertz band. Then we have the MAC header. This is when we're finally getting to the higher data rate that we want to get to. And then, our ACK, is, in a way, it's all overhead. There's no data payload there. There's no Ethernet frame we're trying to get across or IP packet. All of that just to get this tiny little IP packet in the MSDU from one radio to the next, right? This is all extra overhead that we don't deal with on wired networks with Ethernet. It's all something that's required because of the limitations of the spectrum we use. And just to hammer home another point about wide channels and why we might want to avoid them, they actually add to that inefficiency. So far we've only been talking about what happens in a 20 megahertz wide channel. Let's talk about an 80 megahertz wide channel using 802.11ac. So 802.11n, 802.11ac, 802.11ax all support the use of channel widths greater than 20 megahertz. And they all have a few different, they each have different ways of using those. We'll talk about 802.11ac because that's the prevalent technology today. But in order to use the full 80 megahertz channel, in this example from channel 36 through 48, the 36 being our primary, we have to do a clear channel assessment across the full 80 megahertz. And we kind of do that in this successive increase in channel width mode. So we start by doing CCA on the primary channel. Then we check the secondary channel, which we would use for 40 megahertz channel width. And then we check the next 2 extensions that would give us 80 megahertz. This is sometimes called dynamic bandwidth operation. And only some APs will do this, but because it's optional, but some do. This is inefficient though, because we're kind of going serially through our channels, and in those secondaries, it takes a little bit longer than the primaries. Additionally, we've got different signal detect and energy detect thresholds. You can see way out there on channel 48 and 44, energy detect is really insensitive, minus 59 dBm, signal detect minus 72. So we're sort of setting ourselves up for collisions there. And then the next thing we do, we have to use RTS-CTS protection, request to send, clear to send. And again, because our because of the insensitivity in the CCA and the wider subchannels, we are more prone to collisions. So I've illustrated a collision there on 44 and 48. After the interframe spacing, the receiving station responds with clear to send frames only on the subchannels that are available. So in this example, just 36 and 40. And what is kind of cool here is that the RTS and CTS frames actually are transmitted in parallel, simultaneously on the same channels. Well, the RTS are transmitted simultaneously, then the CTSs are transmitted simultaneously. So finally, after we've established that part of the medium is free, we transmit our data frame. So now we're finally getting data across after all that extra overhead. Interesting here, the PHY header still is just 20 megahertz wide. It's just the data payload, the MPDU of the frame, that actually uses the wider channel that we wanted to use. In this case, it can only use 40 megahertz because we had collisions with our RTS. After that, another ACK, again, just on the 20 megahertz wide channel, and then we can start contention again. So not only do we add all this overhead to EDCA, and we require RTS, CTS protection, which is inefficient, but we're using the spectrum inefficiently. There's just this tiny sliver of the data payload that's going to use the full amount of the channel that's available, so it's inefficient. All that said, one of the great ways to think about this is with this graph that comes from us, from Keith Parsons at Wireless LAN Professionals. When we're designing, we've got areas of RF that we want, we don't want, and we just don't care about. We can simplify all that into these three areas in our designs. So if we think about what we've got here, we've got two APs on channel 1. So there's potential for them to contend for the channel, and their clients to contend for the channel, and for there to be co-channel interference. If you think about it from the perspective of the AP on the left, with the purple colored RF, we have this area where we want coverage, and we want our clients to be. The signal strength is above neg 67 dBm, so we've got the potential to use the highest data rates available, and the RF from the green AP is down below the noise floor, so it's not going to trip preamble detect or other contention mechanisms. The area we don't want is there in the middle, where our signal strengths are so low that we're going to shift down to slower, lower data rates, and the RF from each of the APs is loud enough that it will trip our clear channel assessment. And then now every client of both APs is contending for the channel at the same time in that area. And then the area we don't care about from the perspective of the purple AP is where its signal drops below the noise floor and is no longer able to be demodulated. So what this looks like and one other point here, this is where this concept of ghost frames comes into play, because if a frame is modulated with a high data rate, but we're in a location where we can't demodulate that data rate, but we can demodulate the preamble, that's going to trip the clear channel assessment signal detect threshold. But we will never see those frames. We don't actually know they're there. If we were running a packet capture, we would see no frames, because the packet capture is everything from layer 2 up that we can demodulate. The preamble that's going to trip signal detect doesn't get passed on to Wireshark for us to see. So these are quote unquote ghost frames. So nothing to be afraid of, normal part of Wi-Fi, but that's an explanation of what people mean when they talk about ghost frames. So what does this mean for our, for designs, for the real world? Well, here's an example of a very large floor of a office building where we've got two APs that are both going to be on the same channel. So I've only got one AP turned on, and it's in a hallway, and you can see its RF spreading, shooting down those hallways really, really well. And we've got these yellow and green areas. That's the want area, the area we want. Signal strength's very high, and we can use those higher data rates. It's that gray area where contention occurs, but our signal strength is so low that we can't use high data rates. We certainly, though, will affect EDCA with other stations operating on the channel. So if we turn this other AP on and it's operating on the same channel, even though these APs are hundreds of feet apart, now we've got this big don't want area where the signal from both APs is loud enough that we're going to trip our CCA thresholds and cause contention. That's no good. And one of the reasons this is happening is because both of these APs are in the hallway. So if we use some better design principles and put these APs in the rooms, look at that. Suddenly our contention areas are contained. They're not just shooting all the way down the hallway across the whole building. We also have better signal strength in the rooms where the clients actually are. We don't always, why do we need to have high signal strength out in the hallway? We need it in the rooms where people are. And then but the important point here from what we're talking about is there's no overlap. There's no don't want area here anymore, where clients in either cell are going to hear the transmissions from each other, and then we have a single collision domain. So really important design considerations that understanding the arbitration process and the distance that preambles can be demodulated at, it really makes it important to break up contention domains to help us avoid CCI, even when it's hard to detect. We want to do as much as we can to limit co-channel interference. And if we can do that and have more contention or collision domains, we'll have more net capacity, because now more stations can transmit simultaneously if they're in separate collision domains. Smaller channel widths enables that, and because of the issues we talked about, particularly the CCA signal detect threshold, CCI is always a bigger issue than it may appear. And one last thought about design I want to leave you with. We only considered the transmissions from these access points when we're looking at the site survey. But of course, clients transmit too, and they're not directly underneath the AP. So imagine clients at the edge of these cells with their own transmissions spreading out in different ways. That's client-induced CCI, which actually has a much bigger range than AP-created CCI does. So think about that when you're doing designs too. One thing we didn't talk about, and I'll just mention a few things here, is Wi-Fi 6 and 802.11ax. The headline feature is OfDMA, which is marketed as a way of turning our channel or Wi-Fi into a switch, or operating in a switch-like fashion, where many stations are transmitting and receiving at the same time, just like Ethernet can do with its with switching. That's not what OfDMA does. A better analogy is an air traffic controller. where we can orchestrate the landing and taking off of multiple aircraft on the, at the same time. But, without the air traffic controller, we're going to have collisions, and it's going to be ugly. And the other thing to keep in mind about OfDMA, for it to happen, first, the access point has to win the channel using the EDCA process that we talked about. So it has to go through a clear channel assessment, the nav timer, the interframe space, the contention window, and then when it gets the opportunity to transmit, it says, okay, now we'll do OfDMA, and I will orchestrate and schedule channel access between multiple stations. So EDCA does not go away because of that. And then some really advanced topics that that alter contention in Wi-Fi 6 as well are spatial reuse, where now we can have separate clear channel assessment thresholds for overlapping BSS transmissions. And we have 2 nav timers, one for our intra BSS frames and one for inter BSS frames. So if you want to learn more, Google those terms and you will go down some rabbit holes. But I think that's a little bit more than what we'll talk about today. So, okay, I think we covered the basics. And Kelsey, I don't know, do we have a little bit of time for a question or two?
Yeah, thanks, Jim. I think we have time for a question or two. We have our first one that came in from Jason, and he would like to know, for CCC, how quiet should a neighboring AP be if on the same channel?
Yeah, and I like CCC as an alternate to CCI. So CCC, we're talking about the same concept, but he's saying instead of interference, we should call it contention, co-channel contention, because that's what it is. We hear the preamble, we back off, we're politely sharing the channel. We're not transmitting at the same time and causing collisions and interference. But how quiet should a neighboring AP be if on the same channel? It depends. There's no single answer to that. As quiet as possible, I would say. Use all the channels you can until you have to reuse them, and put that that second AP on the same channel as far away as possible. But if it can be, access point radios especially are extremely sensitive. So, if you can get down into the neg 90s and below, that's a design I'd be pretty happy with.
Awesome, thank you, Jim. And I think we have time for one last quick question from Mike here. He wants to know which frames are not ACK'd.
Okay, so which frames are ACT and which frames are not ACT? So all unicast frames are ACT. Broadcast and multicast frames are not ACT, which would include beacon frames and like a multicast video stream, and certain management frames coming from the AP that is going out there. RTS, CTS are not ACT. The CTS is sort of the response to the RTS. So if you don't get a CTS back, the channel is not free.
All right, thank you, Mike. Thank you, Jim. And thank you to all of you for tuning in today to another great episode with Jim Vada. Really thankful that you all tuned in today. And we hope that you'll join us next Wednesday for another episode of our Best Practices webinar. Have a great day, everyone. Thanks.
Thanks, everybody.